Hello everyone, welcome back. Today in this video lecture we are going to discuss the number of atoms present in unit cell. This is in continuation with the unit cell and its classification. So we know that any crystal lattice is made up of very large number of unit cells, and every lattice point is occupied with one constituent particle. We have classified them in mainly two categories. One is primitive unit cell, the other is centered unit cell or centered cubic unit cell. Centered unit cell or centered cubic unit cell is further subdivided into three categories, that is BCC, body centered, second FCC, face centered, and third, that is end centered and abbreviated as ECC. So we shall consider here only main three types, that is primitive, body centered, and face centered cubic unit cells for the simplicity of their constituent particles. First we are going to learn the primitive cubic unit cell. Now just imagine a room or a classroom where you are sitting. The classroom has upper four corners and lower four corners. So primitive cubic unit cell has atoms only at the corners. Just recall the memory that what is a primitive unit cell. You can see here, this is a simple cubic cell or primitive cell where the lower four corners and the upper four corners are occupied. So what happens with this? Each atom at a corner is shared between the 8 adjacent unit cells. Now you can see this is a figure 1.8. Now if you are making a three-dimensional structure, then these 8 corners, each 8 corners are shared with other 8 adjacent unit cell, and that's the reason figure 1.8, where the 4 unit cells in the same layer, these lower layers 1, 2, 3, this lower one 3, and this back one, this 4, the lower fours and upper fours 1, 2, 3 and 4. So this 4 unit cells in the same layer and 4 unit cells of the upper or lower layer, and therefore only 1/8 of an atom or molecules or an ion actually belongs to the particular unit cell. Now this you need to remember that when a corner is there, corner has the contribution to the unit cell which is equals to the 1/8 of an atom. So you can see this figure 1.9, where a primitive cubic cell has been depicted in 3 different ways. So this is a simple cubic where lower 4 corners and upper 4 corners are occupied. These are the atoms. So you can see 1, 2, 3, and that's backside 4. The lower 4s and upper 4s. This 5, 6, 7, 8. Okay, so these are the corners which are being occupied. Now actually what I mean to say, what I am trying to say, that only 1/8 of the atom is actually contributing. Now you can see this is a 1/8 part of each 8 corners, which is actually contributing and making a cubic cell. So this is figure C, is actually the portion of an atom belonging to the 1 unit cell, which is actually the 1/8 part of the original atom which is occupied at that particular corner. So the arrangement of the particle is easier to follow in the open structure, and that is depicted in the space filling representation of the unit cell, which is actual size. So now you can see in between this there is some space. If you carefully observe, some space you can observe, that is called the void or hollowness, and the maximum capacity of occupying the unit cell particularly is defined as the packing efficiency. The packing efficiency is what you are going to learn in the next video lecture. So for now you can remember this: since each cubic unit cell has 8 atoms on its corner, the total number of atoms in one unit cell will be 8 into 1 by 8 equals to 1 atom. So if someone asks you that how many atoms are present in a primitive cubic unit cell, your answer will be 1. Okay. So now moving to the next topic, that is the number of atoms present in body-centered cubic unit cell. A body-centered cubic, which is abbreviated as BCC unit cell, has an atoms at each of its corner, and one atom is present in the body of the center. So if you carefully see the figure 1.10, which is actually showing a body-centered cubic cell, you can see the lower 4 corners and the upper 4 corners are occupied. Along with these, all are in together lying with the one atom which is actually in the center. So if you are taking actual portion, what is the contribution of what is the contribution of these atoms which are present at the corners? The corner has the contribution which is equals to 1 by 8. But when you are talking about the atom which is present at site in the center of the body of the cubic cell, the contribution of that particular atom will be considered as 1 together. It makes 8 into 1 by 8, 8 corners into 1 by 8 contribution, so it becomes 1, and one body centered atom whole together it becomes 2. So if someone asks you the body centered cubic cell, how many atoms are present, you can see actually figure 1.10 C, which says that 8 corners are occupied with the atoms, and corners are contributing 1 by 8 part, so it is making a corners of that particular BCC, while because of BCC it is having the one atom which is in the site present in the middle of the body or middle of the cube or cubic. It becomes 1 plus 1 equals to 2. Now coming back to the next and the last type of cubic unit cell, as you can see on your screen, the face-centered cubic unit cells. Now this is something very interesting. A face-centered cubic unit cell contains atoms at all the corners and at the center of all the faces of the cube. Now you can just imagine a room or a classroom where you are sitting. Imagine that all upper 4 corners are occupied and the lower 4 corners are occupied. So how many atoms are present at now? 8 atoms are present. Okay, so 8 corners, and what is the contribution of actual 8 atoms? It is 1 by 8. So now you can see here that 8 corners into 1 by 8 atoms per unit cell, it becomes 8 into 1 by 8 equals to 1 atom. Okay. Now, talking about the phases, see, your room or a classroom is having 4 walls. Okay, just imagine with the directions that east, west, north, south. Okay, and it has 2 more phases, that is the ceiling where your fan is there hanging, and the one where you are sitting down, so up and down. So your room or a classroom has 6 phases. Similarly, if you are taking a cube will also have 6 phases. Now carefully observe this figure 1.11 with this purple color. What you can see, if you are placing 2 cubes together, what happens that the face with one common phase, it will be having one common phase, and it will be shared with 1 by 2 of each of the cube. Just imagine 2 rooms or 2 classrooms which are there together sharing the common wall. It's like where we are sitting in the classroom, we are having the classroom just next to our classroom, the neighbors. We are sharing the same wall. It happens in our house also that we are sharing the same wall between 2 rooms. So what happens, where it can be seen that each atom located at the face centered is shared between 2 adjacent unit cells, and therefore its contribution to the unit cell will become 1 by 2 of each of the atom of that particular unit cell. Now you have how many phases? You have 6 phases. So 6 phases into 1 by 2, it becomes 3. Together 8 corners plus 6 phases are contributing to 1 plus 3 equals to 4 atoms. So now you can see this figure 1.2, which actually clearly depicts you the open structure, 8 corners, this upper 4 corners and lower 4 corners, then 6 phases, 1, 2, 3, 4, 5 and this 6. So the 6 are occupied, and if you are placing in 3-dimensional structure, the 6 phases will have the contribution to 1 by 2. That means the half of each atom will belong to that particular unit cell. Now you can see exactly this figure. They should be corrected as C. So A, B and C. So this is actually the correct FCC, which is you can see where 8 corners and 6 different phases, this 1, 2 and 3. Similarly, 1 will be at downside and 2 will be on the other side. So these 6 phases are contributing to that particular face centered cubic cell. So if someone asks you how many atoms are present in face centered cell, so you can say there are 4 atoms present in the FCC. Now after this discussion, let us revise this topic. That each corner of a unit cell in a crystal is associated jointly with 8 unit cells, hence its each edge of the side is associated with 4 sides of the unit cell, and each phases with the 2 unit cells. So if you are taking the calculation or we are finding the number of atoms present in the unit cell, what will be the calculation? That 1 by 8 part, this is what you are actually going to remember, that the 1 by 8 part is occupied by corner, 1 by 4th part by edges, and 1 by 2 path by phases. This 1 by 4th path of the edges I have not cleared yet. This is I am going to cover in upcoming videos, where you are going to learn the octahedral voids and tetrahedral voids in 3 dimension, where you will be needing this 1 by 4th path of edges. For now you have to accept that for corners it is 1 by 8, for edges it is 1 by 4, and for faces it is 1 by 2. So finally this is summarization of this calculation. How we have calculated for simple solid crystal or cubic crystal, it becomes 8 corners into 1 by 8 equals to 1 atoms. For body centered, all 8 corners are occupied plus 1 atom in the center of the body, so it becomes 1 plus 1 equals to 2. And in the face centered, it becomes 8 corners plus 6 faces, and faces have the contribution equals to 1 by 2. So 6 into 1 by 2 becomes 3. So 1 plus 3 equals to 4. You can take a screenshot of this table. Simple cube has how many atoms? 1. BCC, body centered, has 2 atoms, and face centered has 4 atoms. Take a screenshot. This will be very useful to us for the calculation of the packing efficiency. So I hope this is clear to all of you for watching this video. Thank you. Thanks for watching this video. I request you to complete chapter 10 as soon as possible, and please start learning chapter 1 along with these videos. Thank you. Thanks for watching this video.